Okay. So single electron transistor is a nano transistor. As shown in the picture here, it consists of source, drain, and a metallic ion or quantum dot in between. Two gates control the flow of electrons. This device works on the principle of Coulomb blockade effect. Most interestingly, it precisely controls the flow or tunneling of single electrons. Thus, it can be used as a charge-sensitive device for qubit readout technology of positron that underpins Miyahara research. Here on the bottom left is an SCM micrograph of charge-sensitive device. It consists silicon germanium-based quantum dot coupled with superconducting single electron transistor. Multiple gates TU, L, and R manipulates the transfer properties of the single electron transistor, which will be helpful to precisely detect ambient charges. We know that single electron transistors are prone to the noise caused by ambient temperature. Here is the summary of my COMSOL work aimed at overcoming the noise due to thermal energies. Calculated Coulomb blockade energy supersets the temperature effect. The capacitance required for this is in the order of few attofarads. This table evaluates the feasibility of single electron transistor at room temperature. Electron beam lithography technique has been the go-to method when it comes to fabrication of single electron transistor. Problems: you end up through complicated procedures of fabrication, often depositing the structure 100 nanometer or larger. It is time-consuming and expensive. As a promising alternative, we return our focus to heavy technology, focused electron beam-induced deposition technology. It is akin to taking a pen or bringing a pen and sketching 3D structure onto a substrate. Focused electron beam-induced deposition is a process of dissociating or decomposing incoming precursor gas that leaves non-volatile fragments or substances deposited onto a substrate. Here in the picture, it shows that an incoming electron beam dissociates the precursors of gas. In our case, we use trimethyl cyclopentatediol platinum. Platinum gets deposited and the volatile fragments such as carbon dioxide or water are entered into the chamber. This technique incorporates high spatial resolution, sub 10 nanometer region. It is a direct 3D deposition process. Most important of all, it doesn't require a mask. However, this deposit contains massive amount of carbon, 71% or higher. We have a challenge. Our nano structure, nano deposits are plagued by carbon contamination, which makes our structure often dysfunctional. Thus, it requires optimum post-processing technique in addition to deposit nanostructure, tightness, thinness in the world. Yes, every triumph comes with its challenges, and the challenges propels our study purpose to eliminate carbon contamination and transform this structure into metallic wonders. In order to deposit these nano wires using heavy technology, The key parameters that we often come across are operating voltage, beam current, pitch values. These parameters should be optimized since they significantly impact the deposition. Plot here shows that volume per dose decreases with incident electron beam energy stabilizing after 15 kilovolt. It means volume per dose in 1 kilovolt is 4 times higher than that at 30 kilovolt, which is further illustrated by this picture on the right. The electron beam, incoming electron beam with high apparent voltage, penetrates the substrate deeper, reducing the contribution from backscattered electrons, secondary electrons to the deposition process. This understanding lead us to the findings to choose operating parameters as operating voltage 2 kilovolt, beam current 23 picoampere, pitch value 1 nanometer, which will be discussed further more. And the deposition time to deposit nominal thickness wire 2 nanometer, 200 nanometer of 1 micrometer length requires 1 second to 200 seconds. Scientific community around the globe has been dealing to reduce carbon contamination. They practice electron irradiation as in A, heat the substrate in presence of oxygen and hydrogen in addition to electron radiation as shown in B, blow water vapor in addition to electron radiation like in C. The method D introduces pulse oxygen at 150 degrees Celsius. Highly scientific practices though. Our endeavor to reduce carbon contamination took an unconventional turn. We use annealing chamber or microoven in our Miyahara's lab, heat our samples containing nanostructure to a temperature about 375 Kelvin for about 4 hours. This slide shows a sample on the bottom left prepared by Ujjwal using electron optical lithography technique. Platinum nanowires are deposited to connect these adjacent electrodes. SEM micrograph here shows number of black spots. A zoomed in view shows that deposited platinum nanowires. On the right, you see 2 black probes of corners being landed on the electrodes. It's ready for IP measurements. And here in the middle, our black sample sits on the top of PPMS POC, Physical Property Measurement System POC. A close observation tells that this tiny gold wire that runs from my sample to 4 terminals of the PPMS POC. This setup allows us to make a measurement of electrical resistance at different temperatures. Here are the number of instruments that I have used in my research work. SEM is used for heavy deposition, high resolution images, and for ADS analysis. Similarly, the corners was used for IV cup measurement and several other electrical characteristic measurements, whereas PPMS is used for taking electrical resistance at different temperature. Wire bonder helps to complete the circuitry between my sample and the circuitry of the PPMS POC. Broker FM, AST FM were used to take FM topography and CBD contact potential difference measurement using KP FM technique, Kelvin probe force microscopy technique.